Welcome. Today, we are going to explore the fascinating concept of combination of pulleys. You already know that a pulley is a simple machine used to lift loads. But a single fixed pulley only changes the direction of force, it doesn't reduce the effort. So, what if we want to lift a heavy load with much less effort? That's where combinations of pulleys come in. By arranging pulleys in systems, we can multiply force, distribute the load, and make lifting easier. You've seen this in real-life cranes at construction sites or elevators in buildings use pulley combinations to achieve efficient lifting with small efforts.
Now let's talk about the mechanical advantage of pulley systems. Mechanical advantage, or MA, is defined as the ratio of load to effort. In a pulley combination, MA increases as more pulleys are added. In the ideal case, mechanical advantage equals the number of rope segments that are directly supporting the load. Next, we have velocity ratio, or VR. This is defined as the distance moved by effort divided by the distance moved by load. And efficiency, represented by the Greek letter eta, is given by the formula efficiency equals mechanical advantage divided by velocity ratio multiplied by 100. So in short, more pulleys mean more advantage, at least theoretically.
One of the most common pulley combinations is called the block and tackle system. It consists of two sets of pulleys. One block is fixed, while the other block is movable. The load is attached to the movable block and effort is applied to the free end of the rope. The key idea is this: the number of pulleys in the system equals the number of rope segments supporting the load. Therefore, the formula is mechanical advantage equals N, where N is the number of pulleys in the system, assuming it is ideal with no friction. This is why block and tackle systems are used in ships, construction machinery, and even in theater stage equipment. Let's now understand the velocity ratio in pulley combinations. For an ideal block and tackle system, the velocity ratio equals the number of pulleys, which is N. Here's the reasoning. Suppose the effort is pulled downward by a distance d. Then, each of the N rope segments shortens by the same distance d. As a result, the load moves upward by only d divided by N. Therefore, velocity ratio equals distance moved by effort divided by distance moved by load, which gives d divided by d over N, and that equals N. This simple idea explains why multiple pulleys can reduce effort while increasing displacement. Now, let's step into reality. In real pulley systems, friction plays a role. Friction in the pulley axles and stiffness of the rope reduce efficiency. This means that the mechanical advantage is actually less than the velocity ratio. Also, as we increase the number of pulleys, friction accumulates, so efficiency goes down. For example, a system with 4 pulleys should ideally give a mechanical advantage of 4. But in practice, it may be only 3 or even less depending on friction. The formula for efficiency remains the same. Efficiency equals mechanical advantage divided by velocity ratio multiplied by 100. That's why engineers must carefully consider real conditions when designing elevators or cranes. Let's apply this to a numerical example. Imagine a block and tackle system of 4 pulleys lifting a load of 800 newtons with an effort of 250 newtons. Step 1. Mechanical advantage equals load divided by effort. That is 800 divided by 250, which equals 3.2. Step 2. Velocity ratio equals the number of pulleys, which is 4. Step 3. Efficiency equals mechanical advantage divided by velocity ratio multiplied by 100. That is 3.2 divided by 4 multiplied by 100, which gives 80%. This calculation shows that the system is not perfectly efficient because friction reduced its performance. But still, it makes lifting much easier compared to direct effort. Let's recap what we learned. Pulley combinations like block and tackle are designed to multiply force so that we can lift heavy loads with less effort. In an ideal world, mechanical advantage equals velocity ratio and both equal the number of pulleys. But in reality, efficiency is always less than 100% due to friction and rigidity of ropes. Yet, these pulley systems are incredibly useful. From cranes that lift steel beams to elevators that carry us to tall floors, combinations of pulleys play a vital role in daily life and engineering. By understanding them, we not only grasp a classroom concept but also connect it to real-world machines that make our lives easier.